everyone, this is Mathical 101, and this is the first video in a series that will be providing solutions to the book Quantum Mechanics and Path Integrals by Richard Feynman and Albert Hibbs. In Chapter 2, titled The Quantum Mechanical Law of Motion, we'll begin with problem 2.1 on page 27, which asks, for the free particle with the Lagrangian m over 2 times x dot squared, show that the action S sub Cl corresponding to the classical motion of a free particle is this expression here. To solve this, let's take a look at equation 2.1, which states that the action is the time integral of the Lagrangian from a beginning time t sub a to an ending time t sub b. If you don't know what a Lagrangian is, it's just a function that describes the state of a particle in terms of its position and the time derivatives of that position. Plugging in the Lagrangian of the free particle into this integral gives us this expression. M over 2 is a constant and so can be taken out of the integral. However, we are dealing with a free particle which, by definition, has no external forces acting on it. X dot, which is a shorthand for the time derivative of position, is a constant since the velocity is time independent and can also be pulled out of the expression, leaving us with this. Next, just like in classical mechanics, velocity is defined as the change in distance divided by the change in time. The change in distance is the difference between x sub b and x sub a, while the change in time is the difference between t sub b and t sub a. That gives us this formula for the velocity, which we can plug into our expression for the action. Notice that this integral on the right here is simply equal to t sub b minus t sub a. This cancels out with one instance of t sub b minus t sub a in the denominator, which leaves us with this simple expression, as desired. And we're done. Let's try this again, but in a way that may be more applicable to other classical action problems. Jumping back to this step, once we move the m over 2 term outside the integral, we can use the integration by parts formula instead. We will substitute u for x dot and du as x double dot dt, dv as x dot dt, and v as x. Integrating by parts gives this expression for the integral of x dot squared. After we plug this in, notice that, since we are dealing with a free particle, the acceleration, or x double dot, is equal to 0. Therefore, this entire integral here is equal to 0, and we only need to evaluate x times x dot at t sub b and t sub a. As we found from our first solution, x dot is equal to x sub b minus x sub a over t sub b minus t sub a. Plugging this in, we then evaluate x at t sub b and t sub a, which leaves us with x sub b minus x sub a. Combining this with the numerator gives us a square term of x sub b minus x sub a. This again yields the desired formula for the classical action, and there we go. That is a complete solution to problem 2.1. Please consider leaving a like and subscribing, and I'll see you next time.